Today we want to talk about what goes into approximating definite integrals, the assumptions that we're making, the core formula that we're using, and how infinity comes into play in this calculation. So let's talk about that. Here is the important thing. We're approximating a definite integral, which is going to tell us the area under a curve and above an interval on the x-axis. And since we're calculating an area, this tells us the important thing that we need to know. Area is length times width. So area is length times width. So the length, so most of the time, we can just get away with multiplying area is equal to length times width because the length is a constant. At this point, all the other formulas that we have for area, we don't need those anymore. Pi r squared, 1/2 base times height, none of that matters. We're going for general areas. We don't need all these niche formulas for these common things that show up. We want to study area in general. And in that regard, it's always length times width. Now, this is all we need. We get to multiply if the length is constant over the entire width. If the length is constant over the entire width, then we get to multiply. So we want to look at the length here. When the length is constant, over the width, then we get to multiply, because it's just constants. But when we're finding the area under a continuously changing function, like this function f of x, we don't get to multiply because the length is not a constant. So when the length is not constant, we have to integrate. So in this regard, we're thinking of integration as multiplication in which one of the factors is variable. So in this case, we're looking at the length being variable, and so that's when we're going to have to integrate. Integration is multiplication in which one of the factors is variable. Integration is multiplication in which one of the factors is variable. So we're going to think of integration as multiplication in which one of the factors is variable. All right. So when the length is constant, we get to multiply. If the length is variable, then we have to integrate. So we're going to build integration from the idea from the multiplication where the length is constant. So our solution to our dilemma, since the length is all variable, our solution is to assume that the length is constant for a little while over a bunch of different subintervals. So our plan is to view the function as a bunch of constants rather than a smooth line. So our solution, we assume that the length, which is going to be f of x, is constant over some small part of the interval. And that's going to be the width, and we're going to call that some small change in x. We're going to assume that the length is constant for some small part of the interval, and then we will get to multiply. So lucky us, that way we get to multiply. So if I can scroll. The way we're going to look at the function between a and b is we're going to break the interval from a to b into parts, and we're going to assume that the function is constant. So instead of all this change that we see in the function, we're just going to flatten things out. And we're going to view the function as this value in those 2 points, and then this value between those 2 points. So we're going to view the area as, in this case, a pair of rectangles. And we're going to use that as an approximation of the area. So here's what it looks like when we assume that f of x is constant. We're going to use one value for the function, and then that's going to be for some change in x. So here we have 2 delta x. That's going to be our width, and then we picked 2 values for the length. Any questions? So we have length, and our delta x are going to be the width. So what we're doing is we're just evaluating the function at some point. So we're just evaluating the function at some point x, let's say x1, and then evaluating the function again at another point, let's say x2. So the lengths are f at x1 and f at x2, and the widths are both delta x. So I just do length times width, f at x1 times delta x, and f at x2 times another delta x. And then we just add them up. Any questions?
If we're not given any numbers, which in this case we're not, how would that be the final answer then?
This wouldn't be a question that you wouldn't have to be doing this question without numbers in it. This is just me demonstrating what's happening in the problem. So this is ideas, not problems. All right. So this is the process that we're going to do things. Where we want to do, the reason that we're going to make this assumption is that when the length is constant, we get to multiply. And that makes calculating area simple, length times width. The problem is that the length is all variable. So we need to take that complicated version of the problem and break it down into the simple version of the problem. Go from variable length to constant length. That way we get to multiply length times width. So that drives our assumption that f of x is constant over some small part of the interval. The next thing to notice is that if we do this more often, if we use more rectangles, then our approximation will be better. So we'll switch pages. We can improve our approximation by using more rectangles. We can improve our approximation with more rectangles. The notes are going to be scanned, so you don't need to write everything down. We improve our approximation with more rectangles. So if we look at the same function, we're going to increase our processing power. So we have the same function, and we're going to be between the same values. But instead of 2, where before I broke this into 2 rectangles, I'm going to break it into 4. So now our delta x is smaller, but the number of rectangles is larger. So each of these is a new delta x. And so on each of these widths, now we've got 4 widths. So on each of these, we're going to pick a value of the function, and we're going to flatten it out. And what we notice is that we've got a lot less error. We've got a lot less of these little bits that have been lost and gained. There's smaller amount missing. So whereas in the first version, we had 2 rectangles and we had these big chunks missing, those chunks are now much smaller. And our area, we now have 4 different values. So we have f at x1, 4 different areas. F at x1 times delta x, f at x2 times delta x, f at x3 times delta x, and f at x4 times delta x.
I know this is just a generic example, so obviously then it's the exact same thing for lower or upper hand estimations.
But yes, this is the same process for lower and upper. So lower and upper just means I would take a lower value, the lowest value of the function, and use that for the whole interval. An upper approximation or an overestimate would be use the largest value and use that for the whole interval. So we improve the approximations with more rectangles. And this is where infinity comes into it. Since we improve the approximation with more rectangles, that tells us that we can approach the exact value with an infinite number of rectangles. So since this is calculus, so we're going to use an infinite number of rectangles to get the actual area, the exact area. Any questions? So what's happening here is that we're using an infinite number of rectangles to find the exact area, because more rectangles means more accurate or closer to the exact area. So an infinite number of rectangles should give us the area that we're looking for. And so what's happening is I'm not sure what I can do about the blurriness. I guess I could try moving it closer. So what we're doing is we're going from a discrete calculation where we have all these different pieces, where we have four discrete rectangles, and we're switching over to a continuously variable region. This one got blurry because I smudged it with my hand because I was trying to move things. So sorry about that. These are going to be blurry forever. So we're switching from a discrete sum to an infinite sum. So we have a finite number of rectangles. We're looking at a discrete sum. Where we have a finite number of rectangles. And then we want to go to an infinite number of rectangles. So we go from a discrete sum with a finite number of rectangles to a continuous sum that has an infinite number of rectangles. This just says now with four widths. I'm not going to be able to erase. Any questions? Let's pause the video here. And talk about what's next.